Yeah, hi everyone. Welcome to Prop Stats 7. So in this class we'll be looking at sampling techniques, and also we'll look at another distribution called uniform distribution. So in the previous one we saw about the frequentist flow rate, and we also saw the binomial and Bernoulli distribution. Obviously, there are many kinds of distributions. Um, we'll be looking few of them in this series. So the goal of this, or rather today's agenda, is we'll be looking at the uh, prerequisites, or rather the steps that we will do prior to selecting a model and calculating probabilities and all that stuff. So we in the last class we saw the frequentist flow rate. We defined the random variable, which could be discrete or continuous. Then we build a theoretical model, which is our Bernoulli binomial. That's what we saw. Then we calculate the theoretical predictions, which are PDF, PMF, CDF, and then expectations, all that stuff. And then we do theoretical versus empirical comparison, like if the model is matching reality. And then if it is, then all great. And if it's not, we refine the model, we tweak the model a bit, we probably restate our assumptions, all that stuff. Now, prior to this is I don't know if I said it in the last class. Anyway, I edited the video because I think I did not mention this. But we do this when we already know the population parameters, or rather when we know the parameter values. Uh, so when we so and generally parameter, like I am pretty sure I said this in the previous class, parameter values are generally unknown, but we do this procedure when the values are known. Now the in this class we will see the procedure when parameters are unknown, which is generally the case, right? So we and when I say parameter, it is the true unknown value, which is basically, if you are, let's say, studying a system and you want to know how much traffic, let's say, taking the previous classes example itself, how much, or rather, how many vehicles um, cross this junction in this in that in that junction. Like if we use the traffic signal example, which is the Google Maps, if let's say we want to know how many vehicles pass this junction, and that will be in probably millions, right? You won't be knowing everything, and that value, that how many, that random variable value is your the thing that dictates the random variable value is your true unknown. It's the parameter, right? It's let's say um, hmm, um, how do I put this? Hmm. So let's go by the same analogy we went in the last class. So parameters are the knobs of your system. So the best example is in the radio. If you change the knob, which is your if you tune the signal, the song changes basically, right? The sound changes. You jump into a different channel and somebody speaks something else, or maybe they are singing a different song. So um, So just think of it this way. So the parameter is the um, um, is one of the main things that you want to know. Let's just put it that way. It is the true unknown which you are trying to predict, but generally you can't because there's just too many of them and you don't have that much time or those many resources. So you take a sample of it. That is where you take a sample of it, you take a small subset of that entire, let's say the traffic, the amount of vehicles that are passing in that junction. You take a small subset of them, like maybe if there are like millions and millions, you take like maybe 1,000 of them, and then based on this 1,000 data, you make the predictions on the entire system. Let's look at the, let's go with the flow. I think as and when the concepts come, I will elaborate. So the goal of sampling, like I said, in this, if we take the same junction example, the number of vehicles passing, that will be our random variable. But say the average rate of vehicles passing through that junction, that will be like our parameter, which controls the distribution. So the goal of sampling, or rather the goal of sampling is basically you have a lot of let's say you have a question saying how many vehicles pass through this junction. Now you want to know, you want to find out this question. But it's actually not feasible to count each and every vehicle that's passing through this junction, right? There's just too many of them. So there's millions of them, and for practical reasons, you don't have the time and resources, like I said. So, so what you do is you take a sample, which is like the 1,000 of them. Again, I already said this, but you take 1,000 of them, but you take 1,000 of them and then make estimates. You estimate the overall population. So the entire thing that you want to know, the number of vehicles that can be your population value. Let me just go with the flow. I think that will be clearer. So that's the goal of this step. So if we see you see here, this comes somewhere over here. After we have our samples, after we calculate the population parameters, we after that we select the distribution, we calculate probabilities, compare empirical and theoretical data, and then refine the model. So this is like the second half of the complete flow. Now we'll look at the first half. The flow actually begins something like this. So we have a question in mind. Okay, so we have a question in mind, and we want to find out how to answer this question. So the question can be, there can be many questions. We'll solve this kind of question sometime later on, but the question can be something like, I want to find out, if we take the junction example itself, how many what is the rate at which, if we take the parameter, what is the rate at which vehicles pass through in this junction. And the random variable can be something like, the random variable is something that changes constantly based on the parameter, right? So the random variable can be something like how many vehicles pass through this junction. Now, so if in this question, what is the parameter? Sorry, what is the population? So the population is the entire vehicles, right? The millions of vehicles that we have. Then, so the definition of population is anything that we want to study to get a particular answer. It's the thing that we are interested in. So the population can be something like, to give more examples, number of emails that maybe your company is getting every day, or every hour, or every minute, or every week, or like we said, number of vehicles passing through a junction. This can be our population. Or you can say number of spam emails that you get in your inbox every day, or or something like number of cars people purchase every year in a particular city or in a particular country. So all of anything of interest that we want to know a specific answer, that can be a population. Now, and the question can be that's the thing that we want to know about that population, right? And if we look at then we find out, we define the parameters and statistics. So a parameter is the value of the population, while a statistic is the value of a sample. So generally, parameter is it's a measure of the population. So when I use the word population, or let me not confuse right now. So it's the measure of the population, and then statistic is a measure of the sample. So sample is the small subset of the population. It's just like a few number of items from the entire set of populations, randomly or chosen in different ways. We'll see the sampling techniques anyway. So that's what these two means. And generally, parameter is unknown. It is unknown by its nature because it's just too big. Simply because it's too big. We have finite amount of time and resources, right? Generally, we cannot. If you are trying to do survey across a country, so assume like in India, like 1.4, 1.5 billion people, right? So obviously, no individual group or large organizations can can ask each and every person. It's just not feasible. So it's impractical. That is why it's unknown. It's not like it is. So that's what unknown means. It's not like it's not knowable. It's just impractical to do it. So it is generally considered unknown because no individual organization or any single person can or generally takes up that entire task. It is unknown, but it is fixed. Fixed means it has a particular boundary. So it's like in India, like we know the number of people there are. It's a fixed quantity. It's not like it's a variable quantity. It's not unknown. So this value is fixed, but it's unknown. This might seem a little weird because how if we already know the fixed value? I mean, um, how can something be fixed and unknown? So the um, it's just that, like I said, it's not just one question, right? About the population, you want to know about their gender or their uh, uh, identity or their preferences, or so many things are there, and it's we just know, like, um, how do I put it? Yeah, just think of it this way. It's fixed in the sense that it's not like infinite. We know that there's a particular quantity, but the parameter is something that we choose, right? It's not just one parameter, right? It can be many things. Like, for example, if we take the population of a country, it can have many kinds of parameters. Like, you can have uh, parameters like birth rate, or uh, um, fashion preferences, or food preferences, or many parameters are there. Those are generally unknown, but the entire population is a fixed quantity. While sample, when we come to statistic, which is a sample measure of a sample measure is generally random, or random in the sense that if we pick like a bunch of people from this place or that place, or a bunch of people from different places, we don't know exactly the it's generally not fixed. That's what it means. This keeps changing. It's changing. The value keeps changing, but it is known. It is known because it's a small quantity, right? We can just count it. We can just make assumptions. It's since by its nature, because it's small, we can just do it. So that's what it means. Parameter is unknown but fixed, while sample statistic is known but random. And random in the sense of the composition is not fixed; it keeps changing. Then if we look at, so the flow is something like, I have a question, right? Now let me just define the population. Then after defining the population, I will choose a sampling technique. So let me just give you an overview of the flow. Then I will choose a sampling technique. Like, how do I choose this particular set of people so that it represents the entire population? So I have to make sure that a particular, like, the sample that I choose is not getting biased or something like that. So I choose a sampling technique. Then I collect the data from these from this sample, right? I collect the data, and then I calculate the sample statistics, which is basically the things that we want to know about the population. We will know through the sample, and then we project these sample values to the population values, and then we use the distribution and do the comparisons. So that's like the general overview. So now let's look at the sampling technique. So when you see the words sampling, what it means is okay. So before that, sampling technique, like I said, it is a way to choose your sample data. Like, suppose if you have a bunch of if suppose this is your population data, your sample can be something like this, or maybe something like this, or maybe one from here, 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 here. You pick all these and make a sample. It's just a subset of your entire population, right? Yeah, so the definition of sampling is nothing but it's what I've already said in the beginning. It's the process of uh, collecting a small sample from. It's like just getting a subset from the population data and then inferring about the population through this sample. That's the process of sampling basically. And there are different types of sampling. One is random sampling, or also called as probability sampling, and the other one is non-random sampling, which is basically you define set of rules to gather the sample data. So if you take the first one, which is random sampling, as the name suggests, it's randomly chosen. So it's nothing but it's as the name suggests. So you just shuffle the, like if you have like a deck of cards, you shuffle and you pick some stuff randomly. Or if you have like a bunch of people, you write their names, put it in a box, just shuffle it, and then pick randomly, right? Yeah. So the idea is every person has equal chance of getting selected. Basically, that's the core idea of random sampling. If we take the example of a coin toss or a dice roll, or that 52 cards, poker cards, when we toss a coin, heads and tails have exactly half the probability, right? Both have the same chance if it's a fair, obviously fair. We're talking about fair coin toss or a dice roll. So a dice roll, you have 1, 2, 3, 4, 5, 6. Any one of these sides have 1/6 the chance of showing up, right? So that's what random sampling means. Each when we perform the selection, every person has or every entity or whatever, everything has an equal likelihood of getting selected. So and in this one there is a subset called simple random sampling. The procedure is something like, we first define the population. So let's say if we take the same example, which is the number of vehicles passing through a junction, then all those vehicles will be our population. Then we find a sample size. So how do we get the sample size? There is a particular formula for getting a sample size. I will share this Colab. This is the formula sheet. So what you can do is we can use the exact formulas to get the sample size. So in this case, where is that one? Yeah, this is the sample size selection for a proportion, and this is generally applicable for all scenarios. And this thing has two sub scenarios. We'll look at the first one. So let us say there are 100,000 vehicles passing through that junction. For example, vehicles passing through the junction. Right, you have a junction here, you have traffic lights, and you want to know the vehicles passing through this junction, whatever. Now, let's say that let's assume there are 100,000 of them that are passing through. Um, there are 4 ways of rather the sample size. Choosing the sample size is dependent on these 4 you can say knobs, 4 indicators, whatever conditions. We want, if these are dependent on how precise we want the actual result to be. Like the precision is based on margin of error, which is like if you want like maybe 5% margin or 3% margin, as the margin of error you want less and less error, you will have to take bigger and bigger sample sizes. Then it's also dependent on how confident you want it to be. So there's something called confidence level, which we'll see in the upcoming classes, but just for now, just remember it for now. Confidence levels, it's also called as, if you want 95% confidence, we can also restate it as 5% significance level. Anyway, you don't have to think about that now. We'll see that in the upcoming classes. Then there's also something called how variable the thing is. These are all dependent on upcoming class stuff. So for now, just this is, I'm just giving you info. You just have to remember it for now. And then there's also population size. Like when the population size is extremely large, and that largeness is dependent on how you select your, or rather how much the sample size turns out to be. So the formula is, again, I will not explain how this formula came up and all that stuff. This is actually from the confidence confidence level. So again, this is something we'll see in the next class. We won't look at how the formulas came up. For now, we'll just understand the general flow, how the real world application happens. So this will give us the sample size. There are some values. This is the required sample size before finite population correction, which is this one. We'll see what that is. Then there's z-score, which is the confidence level. For now, we'll just plug this value, which is, if we want it, the confidence at 95%. We want it to be 95% confident. And what should be 95% confident? The estimate. So we want the sample to estimate the actual population parameter at confidence level of 95%, right? And the margin of error should be plus or minus 5. And if we want even less error, then the sample size will actually increase. We'll see that in fact in the formula itself. As we reduce the margin of error, the sample size necessary will increase. And that is larger sample sizes are good, but if you look at the real world scenario, it's actually a pain, right? You have to do more work to collect samples. You have to spend more resources and more time. So that's why there's this sweet spot or the trade-off that you make. And if you observe here, nowhere there is a mention of the actual population, because obviously this is just a general formula that will give us the sample size that is needed. So let us say we'll take this only, z square p1 minus p over e square. So here z is 1.96. This z score we'll have to look at the table and then get this value, which again we'll see in the next class. P is 0.5. This is something, if we don't know, we just have to plug in 0.5 For now, we'll plug in 0.5. E is the margin of error, which is 0.05. We will see all this in detail. So sample size needed to estimate a proportion with margin of error E at chosen confidence level. So let's calculate this. What it gives, which is 1.96 squared times P is 0.5 into 1 minus 0.5 is 0.5 over 0.05 whole square, right? So if we do this calculation, 1.96 squared is 38416 times 0.5 times 0.5, which gives us 0.9604, right? Then if we do 0.05 squared will give us 0.0025. So this over 0.0025 will give us 384.16. So around 385 samples is all we need to get a reasonable estimate. Now this is when this 385 is sufficient, or rather reasonable, or rather not just sufficient but also optimal, you can say, because sometimes 385 could also be more. You don't have to collect 385 samples if you have if your population data is very less. So this 385 is sufficient if your population is very large. And what does very large mean? Very large means something, if this 385 is greater than or equal to 5% of your population data, sorry, not greater than, if it is less than 5% of your population data, then it's considered, your population is considered very large. But if it is greater than or equal to 5%, then you have a small population, and that is done using this one. So if you see here, yeah, if your sample is greater than 5% of your data, then what we do is we use this formula for finite population correction. Yeah, so something like, so if it is finite population, what we do is, suppose in this case, if we assumed 100,000 is our population data, then if we take 385 by 100,000, that is like how much? 0, 0, 0 will get cancelled there. So 0.00385, which is like, yeah, it is 0.0, which is how much times 100 is 0.3%, right? 0.3% of, is it 0.3 or 0.03? 1 second. So this is what 100 is 0, 0. Yeah, it's 0.385. So 0.3% of your data, which is very less, right? It is clearly less than 5%. So 100,000 is quite large. It is considered a large population. But suppose if you only have like, if we take only like maybe 10,000 samples, for 10,000 samples, what will it be? It will be okay. Let's take 5,000 samples. Not 5,000. 5,000 population is 5,000. So if we do a 385 by 5,000, what will that be? 385 by 5,000. That is 0.077. So if we multiply by 100, so this will be so this is about 7.7% of your population data, right? So your sample size is 7.7% of population data. So in that case, to properly estimate the correct sample size, to properly choose the correct sample size, what we do is here adjusted sample size is n. So this uppercase n is the population size. So population size we chose 5,000 times n naught. We already calculated n naught. We got 385, right? What is it? 384 point. Yeah, we can take it as 385. So I'm doing it here. Let me just check this value. So 5,000 plus n naught, which is 385 minus 1. So this will be so 5,384. This will be 5,385. So 5,384 over 5,384. That doesn't seem right. Hold on. Okay, so I added it. This should be multiplication. So 1 second. So that is 385 times 5. That will be 192. So this should be 1925.23. So 1925,000 divided by 5,384. So that will give us around 358 approx. So instead of 385 samples, we just have to collect 358 samples. So this is like you're almost saving 30 items worth of not 30. How much is this? 60, 70, 80. So 22, 20. So yeah, almost 30. Almost 30 items worth of time and effort, right? So that's how you can be a little more efficient when you are calculating the sample size. Yeah, so once you select your sample size, what you can do is you can perform the selection, which is basically shuffling and choosing. That's where you shuffle and choose. We already saw this, that you can shuffle and choose in different ways, right? You can just drop the names of the people in a bucket and then shuffle it and then pick the items randomly. You can also digitally you can use a random number generator and then pick random numbers by assigning those random numbers to those sample items, right? So after you are done selecting, then you simply collect the data from the samples. Sample, singular, sample. So that is the basic procedure for sampling techniques. That's how you choose and then collect the data. Obviously the next step is collecting the data, but before that we'll see the non-random sampling. So the non-random sampling is similar to, you maybe define some rules or something, like if you have people standing in a row, you just choose the first row, or you only choose the people from a supermarket, or you only choose people from one particular group or something like that, right? You define the constraints. So the thing is, this is easier to do, but your data will become biased. That's the problem. It's not reliable, while random sampling is much more reliable data. The ultimately the goal is to choose a sample that represents the entire population, right? So that is that's the main thing. And then after that, you collect the data. We already saw that here, right? We collect the data, and then we calculate sample statistics. Sample statistics are nothing but your mean, variance, and standard deviation. But there are two types of statistics: one for your population parameters, and one for your sample stats. So these are the some of the things that you want to know, like sample mean, like mean, variance, and standard deviation. Mean being the center of the data, right? Variance and standard deviation being the spread of the data. The reason why you might have a question like, why are these two not the same? Obviously, because population is for the entire unknown data set, while the sample is the known data set. These sample stats are your estimates. We are estimating the population parameters, right? And these two formulas are slightly different. So I'll give you again, like I said, I'll give these values here, formulas later on. I'll attach in the description. So obviously, mean being sum of terms by number of terms, right? We already saw this stuff before. This is population variance. Obviously, it's sigma squared. The spread is in squared units, and the standard deviation is converted back to the normal units. N is number of units. This is the true average squared distance of population values from the population mean. Pretty much the same. This is the average distance of population values from population mean. While sample statistics, this is the thing. Here the n is sample size, while here the n is number of units in the entire population parameters. We are trying to estimate these using the sample statistics. Let's see. I don't think there is much to explain here. The things are pretty self-explanatory. So here x bar is sample mean. Obviously, it's the mean of the sample that you choose, and is the number of items in the sample that you chose, and value of the ith observation. Yep. And then sample variance. Yeah, this is going to be the sample mean, obviously, right? Because you don't have the population. You are trying to find out the population values. So all these belong to the sample. Okay. Yep. So where were we? So yeah. So once you calculate these values, right, then we use these values as point estimates. So point estimation is both a thing and the process itself. So the point estimation is the process of estimating the population parameters using the sample statistics. And we can also say, so we can say something like sample mean is a point estimate for population mean. Same, sample variance is a point estimate of population variance. Sample standard deviation is a point estimate of population standard deviation. This is where we are asserting the statements. It's just theoretical. There's no calculation here. These are our best guesses. So using the sample, we are guessing using the sample values, we are guessing the population parameters. Then obviously after we guess, we have to see if we have to somehow validate, or rather yeah, you can say then we check for something called standard error. There is this step called standard error. We are trying to see how much the guess that we did through our sample statistics, how off it is compared to the population values. Something like, so the definition for standard error is we are trying to find out the variance, or how the sample statistics vary compared to the population data over many samples, not just one sample. So we take many samples from this population, different types of samples, and then we check the variability. Like if suppose let's say the population is 80, the value is 80, and I got my sample value as 78, one sample value, and I took another sample, and that sample gave me 77. 80, yeah, 77, and another sample gave me 89. So all this variability we are trying to check using standard error. There is a formula for standard error as well, which is standard error of the mean is basically sigma by square root n for when population standard deviation is already known. So there are two scenarios. Generally it's unknown. So if it is known, we use the actual standard deviation of the population over square root n being the sample size. If we don't know, we'll use the sample standard deviation over square root n, and this is valid because it is supposed to be an estimate of the population, right? So that's how we do it when we don't know that. Okay, so that's where the concept of sampling distribution comes. Sampling distribution is nothing but you can say it's a standard deviation over many samples. So we take multiple samples and we try to check the variability within those samples, right? So standard, if we take standard error versus standard deviation, standard deviation is within a sample, single sample, the variability within a single sample, while standard error is variability across multiple samples. That's the basic difference. And the whole the goal is to see how much we are trying to quantify the variability of the population versus the sample values that we just computed, right, in the previous step, calculating sample statistics. Then once that is done, there's something called, we check for confidence intervals. I will not will not be seeing that in this class, but there is another step called confidence intervals, which we will see, like how confident we are, like is it 95% confidence or 97% confidence about the calculation that we did. We'll see in the next class. And then after that, there is also the concept of law of large numbers. This is just a theoretical concept. what law of large number says is it's pretty straightforward. As the sample size increases, the sample mean tends to be closer to the population mean. This kind of makes sense, right? So if you see the diagram here, for small samples, the value is bound to be different, right? But if we take a large sample, as the sample increases, its value tends to converge with the population value. So that's what law of large numbers is basically. And till this confidence interval step, this is all the part when you don't know the population parameters. These values, all the sampling stuff is necessary when you are trying to figure out the population values. Once you know the population parameters, this step then remains the same. This is what we did in the previous class. Build a theoretical model. So after we know this, we'll be looking at we'll be selecting a distribution. This distribution is nothing but, you can say, visually we can see the graph and see if our if the real values are fitting our model. So let's say in this class we'll be looking at uniform distribution. So what uniform distribution is that it's the probability distribution where each value is equally likely to occur. In the sense, it's like the dice roll example we just saw before, right? Every value in the dice roll has 1/6 probability, equal chance of getting selected or showing up when we roll a dice. Same with the coin toss, all the fair coin toss, fair dice roll. And distribution models, obviously there are two types, which is discrete and continuous, right? So again, we already saw this in the previous classes as well. So discrete and continuous, the concept is the same. So discrete means you know what the next step is. So the next step of 1 is 2, next step of 2 is 3, etc., etc. But in continuous, you won't know, right? It's these are real values, while discrete is integer values. Continuous is real values. So the next step of 1.1 is unknown, right? You don't know if it's 1.1 or 1.111 or 112. The gap between any two numbers is infinite. So that is where these are the two types of distribution. So in discrete, you can have something like the dice roll or the coin toss or something like that as examples, and in continuous, you can have something like the random number generator. So if I generate a next number in random number generator, it can give me like 1.11 or 1.22 if we set a particular range. The graph will look something like this for a uniform distribution. It will have a flat line. And then and so there is more theory here as well, but I will not go over that right now. For now, just remember that this is the kind of graph you will see. So as the data that you generate, it should conform to this flat line. And this also has several formulas for discrete uniform distribution. Obviously our probabilities are there, right? So PMF, PDF, they are all different. So if for a discrete uniform distribution, let's say we have integers a plus 1, a plus 2, etc., etc. until b. then the formula will look something like this: 1 by b minus a plus 1, where for a random variable, discrete random variable x, right, for one possible value of x. So if we say a for x equal to, let's say 1 or 2 or 3, whatever, then a being the smallest integer value, b is the largest integer value, total number of possible integer values, b minus a plus 1. And for continuous uniform distribution, the so obviously discrete, we take PMF, right? We already saw in the last class this probability mass function. For continuous, obviously we do PDF. We choose a range. On range a comma b, we have something like 1 by b minus a. I will share this formula sheet. You can go through that for now. When we solve the actual problem, then I guess it will be much more clearer. You also have so we saw standard error. Did we see sample statistics? Yeah, we saw, right? Yeah. So continuous uniform distribution. Yeah, we saw. And then there are also properties of uniform distribution. So this is for discrete, mean variance and standard deviation, and for continuous we have mean variance and standard deviation. So why do we have, you can have a question like, why do we have two sets of formulas for sample and for distribution as well? And I think I already answered this slightly, but the reason is simply because these formulas are based on the probability theory. These are the actual model based formulas. So when people say like model is just formulas, that is what this is. These are the model based. These tell us the model data. While the sample formulas, those are just the estimates. They are not part of the model, right? I hope that was clear. Yeah. Then once we have these, we calculate the probabilities, which is actually, they should not be here. Although they are there, yes, you can say, but this is, so these calculating PMF, PDF and CDF, these fall under the calculating the probability step. We already saw this in the previous class as well, right? We calculate theoretical predictions. So this is the place we can ask different questions. Like, what are the chances that exactly 20 vehicles will cross this junction at this particular time? Or what are the chances that exactly 20 to 80 vehicles will pass within this particular time period? Something like that. Those calculations, you can, theoretical calculations, you can, predictions you can do here. And then once you get those, you will compare empirical versus theoretical data. This is nothing, we want to verify our model data with the actual data which we have collected over here, right? All this till this procedure. So till here, till where? Till over here. So once we do the comparison, we will then see if the things are matching. And obviously there is we already saw in the previous class, we saw there's a criteria as well, right, for how much the difference can be, like 2 standard deviations away or something like that. And then if there is a large difference, then we go to the model refinement stage, because we want to know why the difference is, right? So we can say, then we'll ask questions like, is our sampling wrong? Did we collect the data properly? Did we choose the correct model? Are our assumptions right or not? So that is these questions we do, and then we tweak these parameters, and then we repeat the process once again until the empirical and theoretical values are somewhat closely matching. So that is the entire sampling process. Yeah, so that's the theory part. Then we'll probably see we will see the actual examples in the next class. So this question is there, right? If you see, a machine cuts metal rods with length uniformly between 25 and 30 centimeters. So here, if you see, this is a uniform distribution question. So generally, uniform distribution questions, you have the population data given. So you see here, it's already saying a machine cuts metal rods with lengths uniformly between 25 and 30 centimeters. So it's already giving us the range. So the minimum is 25 and the maximum is 30 centimeters. So we already have the population parameter value. So all this procedure of sampling and collecting data is unnecessary, because we already have the data. We already know what the population parameters are here. So the question is, what is the probability a rod is longer than 28 centimeters? So this machine, the question is like, what is the probability that this machine creates a rod which is longer than 28 centimeters? We will we'll see this in the next class anyway. But as you can see, uniform distribution questions, generally the thing that you have to remember is the population parameters are generally given. I hope that was clear. Yeah, and we'll discuss this in the next class. I'll see you in the next one.